Hello, in this video we are going to look at how we can speed up reactions. This is the second video looking at how we can speed up reactions, and we've already looked at how temperature, concentration, pressure and surface area can all be used to speed up the rate of a chemical reaction. In this video we are going to look at how catalysts can be used to speed up the rate of a chemical reaction. So your keywords for this video are catalyst, specific, enzymes, reaction profile and activation energy. So catalyst is what we're going to look at today, and that includes looking at these three words mainly. Now the reaction profiles and activation energy, hopefully you've come across those when you're looking at energy changes in reactions anyway, but we'll have a little look at those as well. So first of all, what is a catalyst? A catalyst is a substance that can increase the rate of a chemical reaction. And by substance, that could be a compound. So potassium iodide is used as a catalyst in the elephant's toothpaste demonstration. It could be a lump of metal like iron and nickel that are used in a lot of industrial processes, or it could be acid, which is used in a lot of organic processes. So it's just any substance that you can put into a reaction that speeds up the rate of that chemical reaction. And importantly, catalysts are not used up themselves during the reaction. That means that you could put a catalyst in, it can do its job speeding up the rate of the reaction, and then you can get that catalyst back out again and you can reuse it. So that makes catalysts really, really useful that they are not used up themselves. So there are a couple of other features about catalysts that you need to know about. So one of them is that catalysts are specific. And what we mean by that is a catalyst that will work in one reaction will not necessarily work in a different reaction. So you put one catalyst in, it will work in one reaction, but it won't work in another. So the potassium iodide catalyst that we use for elephant's toothpaste would be no good in something like the Haber process where you need a metal catalyst. So specific means that they can only be used for particular reactions, so you have to match the catalyst with the reaction that it is used in. Now this means that for some reactions you're going to need to learn which catalysts are used. So in this topic, rate of reaction, we're looking at catalysts in general, but when you come to look at some of the other reactions like the Haber process, then you will need to learn which catalyst is best for which job. Okay, so one more thing that you need to know about catalysts is that enzymes, which you will have studied in biology, are biological catalysts. So enzymes are substances that speed up or increase the rate of a chemical reaction and are not used up themselves, and they are specific. So you should know that when you're looking at enzymes, protease is an enzyme that will break down proteins into amino acids, but protease will not break down starch into simple sugars, into glucose. You need amylase to do that, so they are specific to their function. And so enzymes are substances that speed up reactions inside the body, so they are biological catalysts. So you may have seen something similar to this representing starch molecule, and you should know that if you take a specific enzyme, so in this case it would be amylase, which is specific to breaking down starch molecules using a lock and key mechanism, which you should know from biology, it can break this starch molecule down into simple sugar molecules. So enzymes are biological catalysts. They work inside biological systems to speed up reactions such as the ones in your body, in your digestive system. So in your exam, you will need to be able to define catalysts. So you need to be able to give all of this definition, and you need to know that they are specific and that they only work in certain reactions, and you need to know about enzymes. Now we're going to look a little bit more about how a catalyst is able to speed up a chemical reaction. Okay, so this is all about energy change within a reaction. So hopefully you recognise this sort of diagram where you have energy up the side. Oh, that's a highlighter. So we've got energy on the y-axis, and we've got progress, time, or reaction along the x-axis. And this is a reaction profile. So this tells us about the amount of energy stored in the reactants and stored in the products and how that changes throughout the reaction. So the line on the left, this represents the amount of energy stored in the reactants, and the line on the right represents the amount of energy stored in the products. And as the reaction progresses, so as we go from the start of the reaction onwards, we move from reactants to products, but not in a straight line. So reactions need energy put in to begin with. So we start putting in some energy, so these reactants have got a certain amount of energy. When they've got the right amount, they can then react, and then the line can come back down again. So this graph always goes up before it comes down, because we have to put in or supply some energy to get the reaction to go. And this amount of energy that you put in from where you started off to the very top of this curve, that energy is known as the activation energy. And we know from the last video that to get reactions to take place, collisions must happen with sufficient energy, and they must have the activation energy in order to produce a successful collision that leads to reaction. So if we've only got this amount of energy, the reactants will bump into each other, but they'll be largely unsuccessful collisions. And when you supply the energy, the activation energy, and the reactants have got this much energy now, when they collide, they're more likely to be successful because they've got more energy. When they collide successfully, they produce products. So the activation energy is put in. So there's energy being put in here. We might be heating it up, something like that. And the energy here is being released. Now in this particular reaction, I can see that there is a lot more energy being released than was originally taken in. And I'm hoping that you know the name for a reaction where more energy is given out than is taken in. This reaction is exothermic. So just take a moment to have a look at that energy profile diagram, that reaction profile diagram, to understand what everything is showing you. So as we go from left to right along the x-axis, this is the progress of the reaction from start to finish. So we start with reactants, we end with products. The y-axis tells us how much energy is stored in the chemicals at any time throughout the reaction. So the reactants have stored within them a certain amount of energy. To get the reaction to go, these particles must have the activation energy, so we put some energy in. We probably heat it up. When we heat it up, eventually we get to a point where there's enough energy to start breaking down the bonds in the reactants, get them all separated, and then they can rearrange themselves into products so the reaction starts. So from here to here, energy is released. So where does a catalyst come in with all of this? Well, if you put a catalyst into this reaction, the amount of energy needed to get that reaction to go drops. So the activation energy is smaller. So you can see on the blue line that we're still going up, we're still putting some energy in to get the reaction to go, and then energy is given out, but we don't need to put as much energy in. And because the particles don't need as much energy, then more of them will be colliding successfully, so that you'll get a faster rate of reaction. So you may need to draw this sort of diagram in your exam. So you should be okay with drawing the first bit, a normal energy profile diagram, but you need to be able to draw what the curve would look like if you put a catalyst in, and that's the blue line here. So we're still going up, then we're still going down, but we're not going up as far as we would if we didn't have a catalyst. Okay, so if I move our reaction profile down into the corner for a minute, we can have a look at why this is actually happening. So reactions can go via a number of routes. So if I've got some reactants and they are going to react to form some products, so A and B goes to C and D, this reaction could go directly, so we could take A and B, react them together and make C and D. That reaction would have a certain activation energy, so let's say this original activation energy is A and B goes to C and D. But what if you went via another chemical? Let's have a look at that. So we're still going to start with A and B, but instead of going directly to C and D, we can go through X and Y. Doesn't really matter what we're calling them at the moment. But you can see that we're still overall going from A and B and ending up with C and D. So we're still doing this reaction, but we've gone via an alternative route. And sometimes when you do that, an alternative route will have a lower activation energy than a direct reaction. So if we've got reactions that are taking place in industry that go like this, if we can find an alternative route with a lower activation energy, then we have to find the catalyst that will cause the reaction to take that alternative route. So your answer in an exam for the effect of a catalyst on the rate of reaction is as follows. So a catalyst increases the rate of reaction by providing an alternative route. So that's this, we're going via something else before we get to a final product, with a lower activation energy. So this route only has this activation energy from here to here. the original route has this activation energy. So there's two parts to your answer as to what a catalyst does. It increases the rate of reaction by providing an alternative route with a lower activation energy. If you learn those two phrases, put those in your exam answers, then you should be fine. So that is almost everything that you need to know about catalysts. So just to finish off this tutorial, we're going to look at an animation to show you how it works. So here we've got some particles. We've got the blue reactant and the orange reactant. They are going to react together to give us a product. Now we're going to let this reaction run for 30 seconds and then we're going to see the same reaction but with a catalyst. And to help you to see how the rate of reaction has changed, we're going to get it to draw a graph at the same time. So we've got the blue and the orange reactants here. You will see them colliding, sometimes successfully, and they will react, sometimes unsuccessfully, and they will just bounce off each other. So our graph down here is showing us how many particles of product we have got. So we started with none, and that's steadily increasing. If we leave it running for a little bit longer, we'll start to see the shape of that graph, which you hopefully should recognise. You should hopefully see some particles just bouncing off each other, some particles colliding successfully, and you see the little spark when they react to form a product. Okay, so you can see that the reaction started a little bit faster and is slowing and slowing and slowing down. So that's a typical reaction. Now we're going to put a catalyst in and we'll run it for 30 seconds again. And this is the blue line on your graph. So you can see straight away this part of the graph is much, much steeper with a catalyst, and a steeper line represents a faster rate of reaction. So what the catalyst is doing is allowing some particles to collide with less energy but still successfully produce a product. So without the catalyst, they would bounce off each other, but with the catalyst, because the activation energy is lower, they don't need as much energy to turn into a product. Okay, now 30 seconds wasn't long enough to get that reaction to end, so eventually, because you started with the same amount of product both times, you would end up with them both ending at the same level, the same amount of product particles. So just to summarise what we've seen in the little simulation, this graph represents a reaction without a catalyst, and this one represents the same reaction but with a catalyst. We can see a steeper line here, so this is a faster rate of reaction. This is more shallow, so this is a slower rate of reaction. And the catalyst used here has increased the reaction, the rate of the reaction, by providing an alternative route with a lower activation energy.